Okay, welcome everybody to this morning's INQA seminar. It was good to see many of you at the in-person conference last week in Innsbruck. It was a good conference, I think. Lots of interesting discussions. Now back to the online series every Tuesday, and it's my great pleasure now to introduce Alejandro Montanez Barrera, who is going to talk from Jülich, is going to talk to us today about unbalanced penalization method on the D wave. So Alejandro, over to you.
Okay, thank you. Yeah, the project is improving performance in combinatorial optimization problems with inequality constraints. So this is an evaluation of the unbalanced penalization method that we have proposed before. So thank you. And the outline, I'm going to do a brief introduction about inequality constraints and combinatorial optimization, some methods for handling inequality constraints, and some applications where we use this method and compare it with slack variables, and some result on the wave advantage, and some result on the wave hybrid solver. Finally, just to mention that this unbalanced penalization is already in some software development kits. And finally, some conclusions. So the introductions first, talking about the combinatorial optimization problems, we can say that this combinatorial optimization is just as a field of mathematical optimization where we have a finite set of possible solutions and that our variables are discrete or can be transformed into discrete variables. So we found these kind of problems in, for example, logistics or finance or operations and manufacturing, and all of them, or at some point, can be translated into combinatorial optimization problems. And with this, we have a way to translate them into the quadratic and constraint binary optimization form. And with this, we can solve with, for example, quantum annealing or gate-based methods, some quantum algorithms. And this is just one way of solving this problem, but is the one that interests us right now. So an overview of the inequality constraints. So some problems of this combinatorial optimization, like the beam packing or knapsack uncapacitated vehicle routing problem, or even the turning salesman problem, in one of the formulations have inequality constraint. So we found a usual approach to handle these inequality constraints for classical optimization, and is use slack variables. And in this work, we will present some alternatives. So let's think about one of the most famous examples where we can find these inequality constraints, and it's the knapsack problem. So in this problem, we have some weights associated to some items, and what we want to do is find an object, or we have an objective function when we want to maximize the value of the items that we carry, while keeping some constraints. In this case, v sub I represent the value of the item that I want to bring with me, and the xi represent just the binary variable of decision variable if I bring the item or not. And I want to maximize this term while keeping constant or below some threshold the weight of my items. So this is the inequality constraint that we will find in the knapsack, for example. So in general, well, we have this QUBO formulation that allow us to represent these problems in just quantum algorithms, but these formulations require that our constraints are taken into account like as penalization terms, because as the name of QUBO, there is this unconstrained, so we have to include the constraints as penalization terms. And those penalization terms, what do in fact is just creating some regions where I just avoid regions of when I have this constraint not fulfilled. So for example, here, if we think about 3 items and that the sum of the items is less than the maximum weight that I can bring, so this is a valid solution. While, for example, here I have many items, but all of them has a W2 that is above the threshold or the maximum weight. So what we want to try to do is just avoid regions where I have this W2 because it's just I'm not fulfilling the constraint. So I will add a penalization term to the objective function that includes that I want to avoid this region. Well, for the first case, the W1, I am in a region or I am fulfilling the constraint, so I don't add the penalization. And the second, I add a penalization. So just a recap of what we try to do is just we have some combinatorial optimization problems. We encode these problems using our slack variables to get the QUBO formulation, or we go with this new method that we developed at the Forschungszentrum, where we use the same, use an unbalanced function to represent the inequality constraints. We come to the QUBO formulations and we solve. It could be with QUA if we use gate-based devices or with quantum annealing. Okay, so the first method could be the slack variables approach. So we have the inequality constraints, and what we do is represent just a quadratic term that generates a penalization where we do not fulfill this constraint. But I have to add some additional variables that in some cases are really a bad approach for coming to regions or feasible regions or optimal regions of my combinatorial optimization problems. But in the end, what makes this extra term or these extra variables that I am adding to my QUBO formulation is just create a flat region when I fulfill the constraints. And when I don't fulfill the constraints, I cannot create these flat regions. So creating a penalization when I am not in the region of the feasible solutions. So the problem with this slack variables approach, there are different limitations of it. When we use quantum devices, the first one is that we are limited in the number of qubits. So to include these extra variables, we need more qubits. And the second is that we don't have a fully connected device. So also these extra slack variables creates some extra connections in my QUBO formulations if we go to a second level of abstraction. So here, for example, we have 3 different problems and the number of variables that I need to add if I include all the constraints. So for example, the traveling salesman problem is try to include all the possible subtours in this linear formulation of the traveling salesman problem. In the bean packing is like we have a generalization of the knapsack when we have like not just one knapsack, but like many knapsacks or beans, and the knapsack problem. So in the knapsack problem is not at all a problem, but for other is like, yeah, it grows and we need more variables. So for example, here we have, if we go to the QUBO formulation where we can represent our variables in our problems, like with nodes and the edges representing like the connection between 2 nodes in the QUBO formulations or these quadratic terms that involve 2 variables, we end up having a lot of connections, not only that I need more variables, but also more connections. And like if we want to go to the wave advantage implementing these combinatorial optimization problems, then we could have a problem to find solutions. So what we propose is a new method. We call this the unbalanced penalization because what we try to do is just an unbalanced function that for when I don't fulfill the constraint, make a large penalization, and when I fulfill the constraint, I make a small penalization. And what we can think of first of what kind of function can do this, like we can go to the exponential to e to the minus h of x, where h of x is just the like my constraint greater or equal than 0. So for positive values, the a to the minus h of x, e to the minus h of x is small, but for negative values is not. Yeah, it grows exponentially. So this is what we want to do, but we cannot, of course, we cannot include encode these kind of formulations of e to the minus h of x. because we only have quadratic terms, but we can do an approximation of these functions. So in the end, we can approximate these functions with two terms. And this is like what we did. So in the end, what we end up having is just these two terms, one quadratic and one linear term for the inequality constraints, and with those Lagrange parameters to try to represent or try to mimic what this slack variables is doing. So a large penalization when I don't fulfill the constraints, and a small penalization when I fulfill the constraints. In this case, the limitation of this method is that because we are doing an approximation, there will be a point where it's has less energy than the other points. And for this, we have to tune well lambda1 and lambda2 for the specific problem. For the objective function, try to follow the objective function and not just these penalization terms. So yeah, like in other words, what we want to say is like maybe your ground state or your optimal solution is not anymore the optimal solution of the original problem, but will be close enough that you will end up seeing the a good solution or a good candidate solution for your problem with inequality constraint. So a recap of how to generate this QUBO formulation. So we have an objective function that could be quadratic. We have inequality constraints, linear inequality constraints. So on this weight, so we have the x variables and some specific terms related to the problem and equal to some c. And yeah, we want to satisfy those constraints, and we have inequality constraints also in the way that we already presented. So we solve this with slack variables approach. So we end up having the first term that is just the objective function. And the second terms will be like the equality constraint with lambda 0 or this Lagrange parameter that we should adjust in some way that it is not too large for try to hide my objective function and not too small to find solutions where I don't fulfill the equality constraints. And the same happens with the inequality constraints. So we have three terms here, the additional slack variables, and also we have to tune a parameter lambda1 that adjusts these penalization terms in the same way that the equality constraint. So with the unbalanced penalization, we have the same two first terms, and the last term is just includes two Lagrange parameters that we should have to adjust in order to find a good representation of my original combinatorial optimization problem. So we have to tune lambda1 and lambda2, but we don't have anymore these slack variables. But we will increase the number of connections between my different nodes in the QUBO formulation. So we try to use different solvers to see how it behaves, but just a disclaimer of what we try to do is not to test different solvers, neither to try to improve the solution to the point of giving one of these devices, try to improve this to the limit of what of problem size. It's just a comparison between slack variables approach and balanced penalization approach under the same conditions. So for this, we use JAPC, the way advantage or quantum annealer from our institute with the default values of annealing time, 20 microseconds, and we do samples of 5,000. And also we use the hybrid solver with the default values of t equal 3 seconds and 10 samples. For the Charlie and Salesman problem, for the beam packing problem, just 1 second, one sample. And simulate annealing, we also present some results using simulate annealing, and we use the classical solver Cplex using a library called docplex for the solution of the problem. So the applications that we will see, so the first one is the beam packing problem. So in the beam packing problem, we want to minimize the number of beams to carry on some items. So we have some items and we want to bring all of them with us and we try to look for the minimum number of beans that we need to do this. So in this case, I want to minimize the number of beans where yj represent the bean, and we go to m beans to try to find the solution, and subject to some constraint. So the first constraint is the inequality constraint. So it's similar to the knapsack problem constraint. So we have the weight of the associated to the item I times xij, where this is the decision variable if item I go to bin j, and this should be less or equal to b, where b is the maximum weight of the bin, times yj, which means if I select this yj to as my bin. So yeah, and we have other equality constraint, and this equality constraints is just telling me that the item I should be in some of the bins. So we also have equality constraints and a solution. For example, I have these different items here, and we want to bring all of them. So in the end, I will only need 3 bins to bring all the items, giving a maximum weight here of 15. So, but in the implementation, we will do, for example, if I have 10 items, I will choose 10 bins for my formulation. So this is not a really good approach, but as I said, is not try to benchmark or improve the solutions, but what we want to do is just to compare both methods. So in the second part is the traveling salesman problem. We use the dancing Forschungszentrum formulation. So in this formulation, what we have is just okay, the traveling salesman problem. Try to find the minimum distance for a traveler to go to a set of cities without leaving one city.
Okay, I'm hearing a technical problem. Shanice, are you having the same technical problem? I can't hear Alejandro.
Yes, yeah, I can't hear.
Alejandro,
He's
can you hear?
frozen.
Okay, we'll have to hope that he recognizes this and reboots. Maybe this is a local UCL problem. So, Dennis, can you hear us?
Maybe
yes.
going.
Oh, yeah. I just got to Alejandro that maybe he might want to reconnect. Usually it solves the problem.
Sorry, you're asking.
Sorry.
Ah, yeah. Here we go.
Can you hear me? Okay.
Yeah, you're back now. We lost
can you
you.
give me again?
Sorry, we lost you just
okay.
as you started to describe the traveling salesperson problem. So maybe
Okay.
start.
Okay. Thank you.
That slide.
Okay, we were here, right?
Perfect. Perfect. Thanks.
Sorry. Okay. Yes. So we were in the traveling salesman problem. So in this case, we have the dancing Fulkerson-Junction formulations of the traveling salesman problem. In the end, is the traveling salesman problem. Just try to find a path with the minimum distance to go a set of cities. Just going one city once and not return to the same city. So this is the one of the formulations. This formulation only says that the variables here are the edges, because yeah, we have the quadratic version or the time window where we have that the variables are the like yeah the city at some time, but this is the linear representation. So Cij represent the path, like the distance for going from CDI to CDJ, and Xij represent just the decision variable if I use or not this path. And the constraints are, we have equality constraints where we say, okay, if we are in city, for example, 14, just one path should go out of this city and one path coming to the city. And this is the equality constraints. But in these formulations, we also can have subtour if we only consider these two first constraints. But by the way, is just calling the relaxation of the Charling-Salzman problem, just including those constraints. So if we include inequality constraints that avoid subtours, yeah, we can fulfill the full Charling-Salzman problem. But the thing with these inequality constraints is that they also grow exponentially because we could generate many subtours in the solution. So yeah, so the relaxation problem is just, or the relaxed problem is just the objective function and the equality constraints. What we try to do is, for example, we generate, and this is called the finger in the dike strategy. So we generate a solution with these two constraints, the objective function and the constraint, and we will end up getting some subtours, like in this way, that we solve just the relaxed problem. And once we find this solution, we add one of these subtours to the constraints, and we add these constraints. And because I added the constraint, the new solution that I will find is something different that does not include the previous subtour, and so on. So we go adding one constraint at a time, and we end up at some point finding a representation of the Charling-Salzman problem. That in this case is, for example, this solution, and was adding one constraint at a time. So we will use this strategy in the Charling-Salzman problem, and because we cannot include all the constraints. But if we include one at a time, then we kind of will be a better representation of this. And this is only for testing like the two different approaches to go to this limit. So if we go to the requirements for solving the Charling-Salzman problem, in the case of the this relaxation version of the Charling-Salzman problem, for 15 cities, we need 105 qubits. And for the unbalanced penalization, well, we need the same number of qubits, but the connections, we need more connections. So in the case of the slack variables, because I am doing this approach of this loop, trying to the finger in the dike, to use that technique, it found a solution with 100, like with 3 more qubits to represent one of these constraints. But after I add this constraint or this extra constraint, I cannot find any more solutions. So this is like the limitation of the slack variables approach. But let me, okay, yeah, and this is what we can do right now with the problem. So, and finally, how we find the multipliers. So we start with a guessing. If you remember, we have these multipliers for the QUBO formulations. So for the equality constraints and the inequality constraint, lambda 0 for the equality, lambda 1 and lambda 2 for the inequality constraints if we use the unbalanced penalization. Yeah, so we choose some small examples of the problem that we want to use. In this case, the Charling-Salzman problem. We include the inequality constraint, solve with Gypsy or with the quantum annealer, and find a solution. We can create an objective function. So we try for these problems to find the minimum energy or tune these parameters that find better and better solutions of my problem, and could be in terms of energy or the average energy of the samples that I get in the end, or could be in terms of the probability of getting the optimal solution. So because I have a small problem here, I can see that I have some large probability of getting the optimal solutions of the problem. So I can try to tune the parameter lambda in terms of maximizing the probability of finding the optimal solution. So, and this is the way that we use to find the tune parameters lambda 0, lambda 1, and lambda 2. And we do this iteration many times until we get good parameters for lambda 1, lambda 0, lambda 1, and lambda 2. And in our case of the Charling-Salzman problem, we found these parameters for lambda 0, lambda 1, and lambda 2. By the way, here we use we always normalize the Hamiltonian. After we have this QUBO formulation and translate this into the Ising Hamiltonian, we normalize the Hamiltonian. So some of the results, we use the wave advantage to give results about the bin packing problems. So for 20 random problems with weights ranging from 4 to 20, and the maximum weight of 20. The number of samples here is 5,000. So we only, for each of these 20 random problems, we use 5,000 shots or samples, and these are the results. So at some point I cannot see more solutions because the probability maybe goes below these 5,000 samples. So for 8 nodes, which correspond to 72 variables, I cannot find any more solution, neither with the unbalanced penalization, neither with the slack variables. But you can see that the probability of getting optimal solutions is better with the unbalanced penalization than with the slack variables. In the case of we want to find the optimal solution, that is the plot on the left. But if we want to see like the probability of finding valid solutions, there is the plot on the right. So again, the slack variables is below just the unbalanced penalization for most of the cases, but in the end, there is maybe not enough samples to really see what happens here. But yeah, this is in terms of the wave advantage. So the next is what happens with if we use the hybrid solver. So the same problems, but this time we use one sample for each of the 20 random problems with 3 seconds for the hybrid solver. And in terms of getting optimal solutions, you can see that we will end up getting optimal solutions up to 29 nodes, which correspond to 870 variables. And at some point, the unbalanced or the slack variables approach cannot find any more optimal solutions. And it's the same if we just focus on not the optimal solution, but valid solutions. So again, slack variables approach at some point just doesn't find any more valid solutions, while for the unbalanced penalization, it keeps finding solution up to 29 items or 870 variables. So in the case of the traveling salesman problem, is the same happening. At some point for the slack variables approach, you cannot reach or find any more solutions. In these cases, this probability is only to find valid solutions. And we also use random problems with distance between cities, choose from 0 and 1. And we went up to 500,000 samples for this specific case. And the relaxation is the problem without constraints, without inequality constraints. So for small cases, it's still possible to find solutions for the relaxation version because we don't have many subtours in the solution for this to.
Alejandro, we've lost you again. Alejandro, if you can hear us, please.
Yeah, there is here. This. Okay, can you hear?
Suggest you reboot if you or reconnect to the internet if you can. See if Alejandro is able to rejoin us. We seem to have lost a number of people from Jülich at this particular moment. I sent Alejandro an email. See if that gets through. Here he comes.
Okay, sorry again.
Good to see you. Some technical problems.
Okay, yeah.
So I think we saw the left-hand side of your traveling salesperson slide, but we didn't really see the right-hand side at all. So we lost that completely. So maybe.
Okay. So
Yeah.
here.
We saw it. Start from here. That's perfect.
Okay. So yeah. In case of okay, this is the probability of finding valid solutions, but in terms of the quality of the solution, so we will end up seeing that for the unbalanced penalization is more close to the optimal solution. In this case, the optimal solution, or Cplex, is the reference. So it's the solution of the optimal path. And yeah, unbalanced penalization again is below to the slack variables approach, and the slack variables approach, I cannot find any more valid solutions up to 12 cities. So yeah, this is about and the relaxation that is without including constraints at all, the inequality constraints. So it keeps finding solutions, but in this case, is the solution that are just with high energy, or in terms of the minimum distance, like more distance for the traveling salesman problem. So now, using the hybrid solver, we went up to 26, 45 cities. And in the case of the slack variables approach, at some point we cannot find any more solutions, while for the unbalanced penalization using the hybrid solver, we can go up to 45, and this is still, and this limit is not because I could not find any more solutions, but is because at this point, this Cplex version, I can only go up to 1,000 variables in like the free version of Cplex. So we leave this to this point, and we already could conclude something about like the both methods in terms of increasing the number of cities. And yeah, now with the different solvers, one thing here is that we analyze what happens with the unbalanced penalization using different classical methods, in this case, using Cplex, but this Cplex is the Ising Hamiltonian, or the QUBO formulation of the problem. If I have this Cplex solver here, I have the QUBO formulation in this blue, and we have here the simulated annealing. So with all of them, we can find valid solutions using the unbalanced penalization method. And this is the main conclusions about this. And the hybrid solver is giving some better result, but I didn't tune any of these other methods to improve the solution. But yeah, in any case, it's good to find for finding solution even using classical solvers. So if you want to test this unbalanced penalization method, this is already in the Wave Ocean. in the mode. So you only need to call this. You can create this binary quadratic model, and when you add the inequality constraints, you only have to specify the Lagrange multipliers, and that the method now is the unbalanced. So yeah, we implemented that. So there is the equation. And there is also, if you use maybe gate-based devices, also we have implemented this on this library that is OpenQUBO. And you can also call this unbalanced penalization function. And even it's the Turing-Sussman problem with the linear programming version here. So just some conclusions. We have presented this idea of unbalanced penalization is a new method to encode inequality constraints in combinatorial optimization problems that does not require the use of extra flag variables. Based on the results of the bin packing and the Turing-Sussman problem, we also have tested this using knapsack and portfolio optimization, and it gives good results. So just if you are interested in some of these problems, or just want to test this, you can use. And the results, given like this information that we already have, they are good in terms of quality, quantity, and problem size compared to the slack variables approach. So thank you. And this is like the two papers if you want to look at them. The first is when we propose the unbalanced penalization. Here is the application of the bin packing problem. And the second is the Turing-Sussman problem with the application of the Turing-Sussman problems on the way. Thank you.
Excellent. Thank you very much, Alejandro. Please accept a round of applause on behalf of all attendees. And let's open this up for questions. If anyone has a question, either raise your hand or just speak up. So maybe I can start with a question. So your unbalanced penalization function has this minimum at some weight less than the maximum allowed weight, which I guess is an artifact of the fact you're restricted to a quadratic function. Yeah. So does this sort of bias your solutions towards particular types of solutions, and more generally? Yes, this graph explains exactly what I'm thinking about. So that minimum there, does that bias your solutions to certain types of solution, or and in general, how does that affect things, given that it's not flat in the allowed region?
Yeah, it's a trade-off. We have seen that we get valid solution, but we cannot explore if the solution that we get is not is being hid by the other possible solutions. Like we analyze like the whole spectrum of eigenvalues, and for some of the cases the method gives like the ground state is not anymore a valid solution because just of the approximation that we are doing. But if you tune good the parameters, you will still find good solution. That in any case, for when you have larger cases, what you expect is not finding the optimal one, but finding good solution, or at least some feasible solution. So
follow-up question. I hope this question makes sense. If you look at the distribution of weights that is returned by your solutions using this unbalanced penalization method, is it peaked near the minimum that I see in that graph? That weight distribution of your offered solutions?
This is just kind of the representation of what I think that is like the message, but we are not completely sure about how it looks for each in a specific problem. So this is just a representation, but
okay. Any other questions from any other member of the audience? Well, maybe I ask one more question then, which is one of my usual questions. Do you have any idea what the hybrid D-wave solver is doing? Because I have no idea. Maybe that's my fault, but what does the hybrid D-wave solver actually do?
Yeah, me neither. It's like always that I try to look for information. It's like kind of black box. Yeah, I don't know.
Okay. Fine.
Yeah, but in any case, what we want to see is like if this method, like still, if we use a better approach to find solution, is still giving solutions, right?
Yep.
So,
Yep.
yes.
Okay, there's a question in the chat from Prashasti, who writes, what sort of applications can these solvers have?
Okay.
What sort of applications can these solvers have?
I'm not completely sure about like.
I mean, we saw some applications, which was traveling salesperson, bin packing, knapsack, so on and so forth. Is it rather more general, or are those the only applications you think that are appropriate for your method?
Yeah, the method is general. Like yeah, many problems require inequality constraints. So yeah, this is if you have an inequality constraints and you have the way, or if you have a problem that you can translate into combinatorial optimization and you have inequality constraint, this is a good way, but it's not restricted to a specific problem. What we found is that, okay, we have this application for just general problems, but you can think that, for example, the traveling salesman problem can be applied to, I don't know, package distribution or things like that. Yeah, if you have your specific application, you can use this approach. For example, some people have used this already for collateral optimization, which is kind of a problem in the finance sector. And they had some inequality constraints, and they found that using this approach give better result than using the stack variables approach. So, yeah, it's general, like there is not a limitation in the problem. So only the only thing is like for the specific problem, you need to tune the parameters, lambda 1 and lambda 2. But it's good because we have seen that this generalize well. So if you find good parameters for small cases, for larger cases, it will also give good approximation.
Good, thank you, Alejandro.
Thank you for the invitation. So,
any other questions remaining from the audience? If not, let's thank Alejandro one more time. Thank you. And apologies for the technical problems. And I look forward to seeing you all at next week's seminar. Let me just find out what it is next week. It's on the 21st of November, next Tuesday at 5 p.m. UTC. And the speaker is Lorenzo Rocuto. Good. Thank you, everyone. I'll see you next time. Bye-bye.
bye, thank you.